So hey everyone, it's me Deepak. So today we will be looking into this problem that is called as all nodes distance k in binary tree. And it's not just a problem that we'll be solving. Okay, we are done with this. No, this is the base fundamental. It's like one of the pattern in the tree which can solve many other problems available out there. So before jumping into everything into this, what the intuition was, the another approach was this, that, blah blah blah, yada yada, so stuff. So we'll be looking into the problem today. That is what is provided to us. So we are given with uh binary tree thus, and also a target node means, and also a distance k that is provided to us. So but what I need to do with all these things, inform all this information. So over here what it's asking to us is this. So see here, it's asking that what all nodes are available at a provided particular distance, that is over here in this case it's 2, which I can travel from the provided node that is target. In this case, it's 5. So as you can see over here, okay. So over here, let's 5. From 5, I can go to 3. I can go to 6. I can go to 2. Now to visit this 6 to 3, what I does have, miss what miss I can miss I can travel it by one step, but I need to determine what at distance k what all nodes I can travel. Okay, so this can't be considered. Okay, so but from 2, miss from 5 I would be going to 2, one step down. From 2 I can go to 7, another step down, that is 2 step down. Okay, 7 can be considered in this answer, that I can return or I can visit from 5 at a distance k that is what to us is 2. And from 5 I can go to 2, one step down. From 2 I can go to 4, that is 2 step down in this case. Great. Now from 5 I can go to 3 as well, and now here one step is done. And from 3 I can go to 1, that is 2 step is done. Now so 1 can also be considered, so I don't need to go further because that will be 3 steps. But in the problem is given, that is given to us is just 2, means I just need to move 2 step, that is I need to move k steps. Okay, before jumping into the solution, what's the approach, what's the intuition, yada yada, there are actual use cases as well of this. What are that? Let's say for example you are searching in a whatever your web browser you using, that what are classes or what are gyms or what are restaurants at a distance 10 kilometer or something like that. So this kind of approach or problem can solve, means at the back end this is the solution that is written there, over there. Means there are a lot of examples available out there. This is one of the example that I wanted to share with you. So okay, before jumping into the solution and all this stuff, we'll just simply looking at, means we'll be going delve into it, that what's actually is this, what approach can I go with, why I can go with that approach only, and all the stuff, and what's the limitations and all stuff. We'll be looking into it. So let's look into the detailed example and solution. Great. So over here, let's say for example this is a tree which we would be considering in order to proceed further with our intention building and all the stuff. So over here, what's provided to us? This binary tree is provided to us. This is the target node. This is the distance k. Means up to this distance, I need to go and figure out that all nodes I can travel. Means there are the possibility at this distance provided k. That is in this case it's 2. Great. So we have already discussed that. Okay, 2 means, okay, from 5 I can go 3, 1, 2 step down, 1 can be considered. From 5 I can go 6. From 6 I can't go anywhere because there's no step further. So now 1 is considered till now. From 5 I can go to 2, 7. 7 can be considered, 2 step down. From 5 I can go to 2, then 4. Okay, 2 step down, 4 can also be considered. Now 1, 7, 4 is considered. Now from 5 I can go to 3. I can go to 1. Done. Does it requires to go further to 0 or 8? No, because it is provided to us at distance k only, or on the over here this is just 2. So from 5 to 3, one step. From 5 to, so from 3 to 1 is 2 step. For if I'll go over here it will be 3 step. It doesn't require in our case. So what's the limitation of the tree node is this, as you can see in this as well, and the structure of it. That is, oh yeah, this is a tree node. It has access to its left, its right, means its child. It has access to just its child, means I can only go downwards with this. So the very first thing while looking into the tree problem, that many of developers out there that can think that okay, I will simply going to doing DFS and just, yeah, that's done. Let's try that as well. So okay, from DFS, okay, tree node has access to left and right. It can go downwards. Okay, if you'll be doing DFS, you will be like okay, 5 6, okay, two step can't be done. Okay, from 5 to 7, 7 is considered. From 5 to 2, from 2 to 4, okay, 7 and 4 are considered to be at a distance k, that is 2. But I can't go upwards. There is upward ability missing. Upward movement ability is missing, because as you can see over here, from 5 to 3, from 3 to 1 also is one of the path that I can go, and 1 is also a potential answer. If I would be going with this kind of approach, just now I said that DFS also, so we would be missing certain potential nodes, which should not be the case. That's why DFS fails in this kind of case. uh, this is the thing, because uh, over here node has access to just its left and right. It can go just to its child, but I need also to go upwards and miss parent, and also parent subtree as well. So I need to do that stuff, which I can't achieve in this case. Over here I went from 5 to 3, that is I went upwards to its parent, and tree node doesn't have this ability. It can only go left or child, a left child or right child, I miss either of its child, but it can't go to parent. So miss it denotes that there is only downward movement that I can proceed with. So in order to achieve upward movement ability, I should have something kind of parent referencing. So that is the thing I need to determine. So I can go radially outwards, 6 to 3, something like this. So we won't be missing any potential node that can be reached from the distance k, that is in this case our provided distance k is 2. So in order to do this, I would be requiring something like a parent referencing kind of stuff. Great. And then over here, if DFS fails, then what's the another approach that I can proceed with? So because as you can see over here that this is not a pure tree problem, and also I need to go upward as well. That's the core difficulty, because it's actually a graph problem disguised as a tree problem. And for this, we can go with the BFS concept, because it's best for the distance k kind of problem, and BFS works naturally on graphs, not uh, one direction trees. So because for that I would be having parent referencing kind of stuff. That's now we discussed. So we will be requiring the parent links. Means that means I would be converting the tree into an undirected graph, means not in the actual way, means just for our problem solving kind of stuff. So over here we won't be just having left and right child access, we would be having to its parent access as well. If I would be having parent access, so I can go to the parent subtree, another subtree as well. Because just now we saw that from 5 I went to 3, that is parent access. From 3 I went to another subtree. Means here we can achieve with using this approach that this kind of access as well. It is left, right. We were already having parent access, parent subtree access as well. That's the great thing. And then what I'll be doing, simply I'll be doing the BFS from the target. I would be noticing, okay, what are steps I have done, I have already walked. Means it's kind of I will be having a counter kind of, okay, distance 0 is done, distance 1 is the distance, 2 is done, okay, 2 is done, okay, that is the distance which I would be requiring. Simply return whatever the result I does have at that particular point of time. That's a simple thing which I'll be doing, because we have used DFS over here, because sorry, BFS over here, because DFS explores depth wise, and but distance K requires level wise stuff, and BFS guarantees it. That is, whatever the first time node you reach, that's the shortest distance, which I can just simply uh, get a insight from that. And we won't be solving it in blindfolded way. This is why I'm saying that why this can be the approach, why this can't be the approach. And also BFS over here is the perfect for distance based problems. So before we go to the solution, okay, let's create a roadmap kind of, so that what we can do, and in an properly intuition uh, building, and means in the process of building intuition, and not solving in the blindfolded manner. Okay, so this is step, let's write this step. Step one is that it can be let me write it again over here. Step one, step one can be okay, parent map. I would be requiring parent mapping. Great. And then step two, which we have discussed, is that BFS from the provided target. And then step three is what? I can't do this continuously. Nah, I don't need to traverse the whole tree. This is not a traversing whole tree kind of stuff. I need to stop at distance K and return the potential nodes which I can travel from the provided target node. Great, great. So the very first thing that I would be requiring is this. Okay, so I would be requiring something like this, parent referencing stuff. Great. So here let's say this is denotes parents, means which node has which parent, means which child belongs to which parent over here. Great. And also I need to maintain that what all nodes I have already visited. So let's say this denotes that what all nodes I have already visited. But why I would be requiring this? Let's figure this out. Because let's say you have now we are starting with the target node 5. You traveled, you have traversed 6 2 3. Now in the next step you would be having an access to this 623. You would be doing same thing with this as well, in order to satisfy the provided K. So let's say you are traversing from the 3 now. So you would be having access to 5 1, that's it. But if you will go to this 5, this is already visited now. Means it's like you are going from 5 to 3, again 3 to 5. It becomes a loop. It will become a loop over here. Loop kind of stuff over here. Loop, which should not be the case. This is wrong, because now it will make what? It's like you are going, the step will be 5 6, sorry, 5 3, and then 3 5, and then again 5 will be having access to 3, then 5 3, then again 5 3 would be access to 5, then 5 3 5. So that's why I need to figure it out, that what all nodes is already done, is already processed. So that's why I would be requiring visited kind of stuff to determine, okay, what all nodes is done, and don't need to proceed further with that. Great. So this will denote uh, visited nodes, and this will denote the parents referencing, that okay, which node has which parents. Miss, I hope you got the, but by this time you know, we are already understood why and we are doing all this stuff. So great. And now we are doing a BFS traversal. So we already know that for that I would be requiring a queue. So let's create a queue as well. Great. Let's set this as a queue. which you would be using in this problem. Great. This is the q which we are using in this problem. And okay, so let's there's the result which will hold actual nodes. That in the case it's that is in our case it's 7, 4 and 1 actual nodes at distance k. Great. We would be starting with our target node. What I would be doing is that before moving with this target node, before doing any this traversal, what we have decided, that is step 1, we would be having parent map. In order to determine which node has which parent, I need to do basically a whole tree traversal firstly. And for tree traversal, because at a whenever I encounter a particular node, let's say for example I encountered 7 at that point, because I went 7 from 2, that is we generally do, that is 2's left, that is and 2 dot right, 2 dot left is this node. At that particular point, I have access to the parent. At that time itself, I would be storing it somewhere. That is this which we have decided. That the thing, that the whole intuition which will be solving it is, that's a new thing over here. And it can using this you can solve at the start I said that is the base problem, fundamental pattern in one of the pattern of the tree, which using this you can solve a lot of problem. Let's say for example a burning tree or something like that. Great. So step 1 is that you should have a parent mapping. So let's start with the parent mapping. Great. Let's say you can use any traversal BFS, DFS, in the DFS in order post or tree order. It's completely up to you. Let's say for example I'm going with the BFS for this case. So over here I have access to the root, that is 3. I would be maintaining this map key value kind of stuff over here. Great. So 3 is the root node. What's the parent of it, bro? Is the parent itself of the, which is the ancestor of the whole tree. So the parent would be null. There won't be any parent for 3. Great. So I'll be saying okay, 3 has parent null. Great. 3 has the parent null. Now as I said that I am using BFS over here. So I would be going to this root nodes left and then right, and I will simply go doing this again and again. I hope you are well versed with the BFS simple BFS, a kind of simple traversal. So great. So now I do have access to its left, that is what, 5. Who is the parent of 5? That is 3. Now I'll be going to the right. Who is the right child of this 3? 1. As you can see, just now I came to 1 from 3. So at this particular point of time, I do have access to its parent. At this point of time, I'm storing it somewhere, and this is the parent map where I'm storing it. Great. So now the parent of 1 is 3. Now I would be pointing to 5. Who is the left child of 5? 6. Who is the parent of 6? 5. Who is the right child of 5? 2. Who is the parent of 2? That is 5. Now 5 is also done. This miss is left and right child is done. Now I'll be pointing to 1. Who is the left child of 1? 0. Who is the parent of 0? That is 1. Who is the right child of 1? 8. Its parent 1. Now 1 is also done. Now I need to figure it out left and right. Mapping the pattern mapping for the sixth node. Does it has left? Does it has right? Does 6 has left and right? Nope. Done. I can't move further now. So 2. Now 2. Does it has left? Yes. What's that? 7. Who is the parent of it? Because I hope you are getting it while doing this problem. Try run. That why at this particular time I have access to parent. That's why I'm storing at this particular point only. So at the later part I can just simply fetch this in the constant time from this map. Great. So 7 parent is who? Who is the 7's who? Who is the 7's parent? That is 2. Now does it has right? Yes. 4. Parents of the parent of the this 4 is 2. Great. Now does 0 has left right? No, proceed further. Does 8 has left right? No, proceed further. Great. Now this is the map which I does have over here. Great. This is the parent mapping which I have for now. I would be using this for solving my problem. Now, as you can see, I do have access to left, right, and parent. If I do have access to parent, I can go to its left, sorry, its left or right. That means another subtree of this parent. Now I'm done. Now I can just simply travel, go radially outwards. Now the problem is completely easy for me. So now I'll be doing the actual BFS which we are talking about. That is step 2 BFS from target, and the target is over here is 5. So great. Now I would be, the very first step is that I would be hence offering a queue with node 5. Great. And also now the file is and has been encountered over here. Also this file would be in the visited, because I just now visited in order to avoid the infinite looping kind of stuff. Just now we have discussed that, which will not be the case. And we need to avoid it, because it will ultimately will be having the infinite loop over there, and there will be revolving, and that won't be a perfect solution. Great. Miss, let's say in the real use case, if it is this kind of stuff without visited set, we are implementing this kind of stuff. This is how we seen the example that is nearby, miss all gyms or all restaurants at 10 kilometer distance of me. So it will be showing all the restaurants beside me only, which doesn't even exist. Means they will be in ambiguity and dilemma kind of stuff they will be facing. There are a lot of stuff available out there, because it's not just this problem. There's a another text stack as well. Okay, that's the thing. That's why we would be requiring a visited set over here. Great. So now 5. Does 5 has left? Yes. 6. Is this in the visited node? Nope. So I can consider 6. I can offer 6 in the queue. Great. Does 5 has right? Yes. 2. Is this visited? No, it's not visited. So I can consider that also. I can offer that 2 also in the queue. Great. Now, does 5 has a parent? Let's check this out. Okay, 5, 5, 5. Okay, 5. 5 has a parent 3. Great. Is 3 visited in this? I can just simply determine whether it's visited or not is by looking into this visitor set. Okay, it's not visited. Great, it's not visited. So I can consider that three as well. I will be offering that in the queue. I'll be pushing that in the queue. Great. Now this 5 is done. I won't be requiring this for now. Great. Now the at the pick, what element, what node adders have is 6. The 6 has left? Nope. The 6 has right? Nope. The 6 has parent. Let's check this out. 6 6 6 6 6. Okay, 6 has parent. Over here it's 5. It's 5. Okay, before moving further, whatever nodes I have visited, I need to insert this in the visitor set as well in order to order that infinite loop. Great. So I would be I will be inserting 6. I would be inserting 2 and 3 as well. At that time, at the time of offering the nodes in the queue, at that time itself, I need to insert in the visitor set as well. Great. So the referencing pointer is now 6. 6 doesn't has left, 6 doesn't have right. Its parent is 5. 5 is there. Is this in the visited? Yes, 5 is here in the visited. So I don't need to proceed with this because it's already done. So for 6, I don't have any nodes which can be a potential answer from 6. So I would be removing 6 as well. Great. Now the pick is what of this queue as 2. Now I would be checking whether this 2 has left. Yes, it's 7. Is this in the visited? No. Okay, this is gonna be the potential answer. Insert this in the queue. 7. Now, does 2 has right? Yes, it has right. That is 4. Is this 4 in the visited? No, it's not. Great. That can also be a potential answer. 4. Now, does 2 has parent? Let's check this out. 2 2 2. Okay, this is can be contained in the constant time. That's why, see here, this is useful in this case. Now I can move radially outwards, not just downwards, upwards as well. And from the upwards parents, I can go to the parent subtree as well. Great. So 2 has parent. 5, is 5 visited? Yes, it's visited. So why to insert it again? Great. So simply don't consider it. So from 2 I have 7, and 4 has the potential answer. So this thing has to be in the visited set as well. Great. 7 and 4. Now what's there in the pick of Q? It's 2. No, 2 is done. I need to uh, just now we have encountered also we before moving further I need to remove it. Now what's the potential node over here? It's 3. At the pick of the Q I just have 3. Now does it has left? Yes. Great. Is this present in the visited? Oh, it's already visited. Don't consider it, just move further. Great. Does it has right? Yes. 1. Is this visited? No. So it can be the potential answer. Just simply insert it in the queue. 1. Done. Now, who is the parent of 3? Let's check this out. Oh, it's a null. It, there's miss that denotes that it doesn't have any parents. I can't move further. Miss with 3. So we would be moving with the some another node, and this here 1 is done. So I need to insert this in the visited set. Great. Now after this I need to remove this 3 because this 3 is radially outward traversal is done. Now with the pick, what's there in the queue? It's 7. Does 7 is left? No. Does 7 is right? No. That's just check the parent of 7. 7 7. Okay, parents of 7 is 2. Is 2 already visited? Yes. Don't consider it. So now readily outward traversal of 7 also is done. Great. Now what's access I do have is 4. 4 is in the peak of the queue. Great. And also doing while doing all these things, I would be having access to this distance, that is what all distance I have traveled till now. So over here as you can see, the starting node which we have over here is the target. We have started with the target node 5. We went from 5 to 6 to from 2 to 3. We have processed this 6 2 and 3. Great. As you can see that 6 for we have firstly visited to 5. It was at the distance 0, because from 5 to 5 is the distance 0 only. And then we went to 6 2 and 3, this thing. So after every means traversal in the queue, that is levels, which we would be considered this as the radial level. I would be saying okay, now I need to do the plus plus, that is I have moved one distance further. So now over here what has happened is that one distance has been traveled. So now this 2 would no, this 0 won't be the case, it would be now 1. Okay, one distance is traveled over here. Then from 6 I would be doing radial outward stuff. From 2 I would be doing radial outward stuff. From 3 I would be doing radial outward stuff. I did with 6, I did with 2, I did with 3. Great. Now this thing is done. From this, what I got 7, from 2, that's 4, and then also I got 1 from 3. This thing I got in the another step. So also I need to cancel this out, okay, because I have moved one step for again. So now two step. Then I'll be moving further with the node 4. So what's there in the queue is the 4 node. Before checking this further, that okay it has left or right, whatever it is, I need to check okay what's the distance provided to us as 2, and did I reach there? Yes, 2 reached. 2 has been reached over here. Great. So as you can see that the last element which did pop is 7, and the last to last was 3. From 3 I got what? From 3 left was visited, right I got this one, I inserted it, and there was no parent of it. So what I did earlier is what I just popped it out. Now this thing I had this pop up this out. So now over here as you can see, this 3 also done this 3. This was the zero step, this was the one step, and this I got to, and the second step this thing, and these all are visited, and this is the two step only which I need to travel based on the problem statements, uh, data which you have provided to us. Two is done. So is there any need to proceed further? No, nope. So whatever the nodes we are left with in the queue, that would be the result. As you can see, 7 is at distance 1, 2. Now 4. 4 is at distance 1, 2. Now 1. 1 is at the distance 1, 2. This is the special case for which we have created this parent stuff, because here from 5 to 3 we went to the parent, and from 3 to 1 we went to the parent subtree. So this is also 1 2 3 step. So this was the answer which would be requiring. So in a result which I would be returning is that we'll be simply popping all the elements out until OK is not empty, and then the answer which we would be having with is that will be 7 4 1. I would be returning a list over here in order to determine okay these all nodes are there that can be reached from the provided distance k and provided node over here. In this case, provided target node is 5 and the provided distance k is 2. So this was the uh, whole dry run. Let's see in the actual picture in the code itself. Let's code it out. Great. Let me maximize it so that you can see it in detail. So over here what I would be requiring is that firstly I need to check okay if root itself that is provided to us is a null or what. If it is null, then I don't need to proceed further. I can just simply return here itself. What I will be returning, this is return type over here as you can see is this list of integers. So I should have this thing okay before returning. So here I'll be having a list of integer that I need to return, and let's name it as result. And the implementation class I would be using is that in this case arrays, or you can use anything. I would be using arrays because it's the it uh, syncs with the problem statement. I should not use any linked list or something like that, unnecessarily uh, just for the sake of it. So here I need a result list, and here this result list would be empty at this particular point because I haven't done any processing yet. Cool, great. So before moving further, I should have parents. So I need to create the parent mapping stuff, because we have decided over here in this step one that I would be doing the parent mapping stuff. So for that, I would be requiring what? I would be requiring, let's say, a parent. Let's say name it as build parent, and here for building parent, what I would be requiring the root node, and then the target node which I just have, and also a map here over here. This thing I will be requiring. So I would be passing this map also. We over here we name it as parents. So let's name the same uh, map over here, that is parents. Great. So for this parent I would be requiring map over here. So let's build this that's map. Great. Map, I'll be storing tree node, that would be the key that will determine the child, and another tree node that will be the value that will determine the parent. Great. So implementation class which I'll be using over here is the hash map in this case. Great. But still I don't have this method build parent to make this referencing stuff. So for that I'll be creating a method. Let's say build parent over here. You can use any traversal, you can use in order, pre-order, post order, anything. You just need to figure out what parent child has. So let's say for example I'm here, I'm using q q data structures and also stuff, the to find out the parents that I'll be using over here. That's a BFS at the level of the travel. So here that's so great. Public, I need to return nothing. So void, because I need to figure it out what all parents it can consist of. So here the minimum method name is build parent. What I would be requiring: root node, target, and then the parents. And this target is what? This target is also tree node, and this parent is what? Is the map over here with key value that is child and parent. Great. Now I would be doing the level order traversal over here. Actually we would be doing this target stuff in this in the actual processing. So here I'm doing parent referencing, so I would be requiring parent. Great. So the parent of root initially would be I'm starting with the root node, so that's why it will be null. So great. Or else I can just simply do one thing, that label order I can just simply go with the any in order pre-order. So in order to avoid this hefty lines of codes or something like that, means I can do something like this: if node equals to null, simply return, because it can't be proceed further. Or and then in the parent map I would be putting what? Parents dot put what's the node provided to us. That means here I'm using the pre-order. So firstly root, then left, then right. So okay, so the node provided to us is this, that is the root, and the parent would be this provided stuff. Great. Now I'll be going with this left and then right, because in the DFS we does that only. Great. So over here I'd be saying what? Build parent root dot left is the node, and the parent of this would be root itself now. And also I need to pass this parents in order to update it further. Same I would be doing for the right child as well, that is build parent root dot right. I would be going to the right side, and the parent of this also would be root, and also I'll be passing the parents as well over here. Great. So what it will be doing at the end, I'll be having parents with all the parent referencing stuff. So that the thing I would be doing over here in this case. And also the level order traversal, you can, as you anyone, I'm just showing it for you, so you can get an idea that what all possible approaches are available. If not only this, I can go with another approach as well. So over here you can do level order traversal as well. So let's say for example, if you would be having a for this we will be requiring a queue tree node in order to traverse. Let's name it has queue only, new linked list. I'm using the linked list implementation over here. Great. The initial thing which I'll be doing is that I'll be offering root node, because I have an access to root node only at the very start. I'll be offering root node over here. Great. And then while my queue isn't empty, I will simply proceed. I will be simply keep on proceeding in order to determine what nodes, what parents, relation kind of stuff over here. Great. So the node which I have access to, the very first node, I will be just simply pop it out. Okay, current node will be this, that is q dot poll, which I would be doing over here in this case. Great. Now what I would be doing is that initially root's parent would be what? Null. So here I'll be putting root as the child, and the parent of root is null. Now I'll be proceeding further for with this left and right subtree of the root. So great. So over here I'll be doing what? If current node it has any left child, then only I can proceed further now. If it's not equals to null, in that case only I would be saying okay. In the parents I would be saying okay, this child, that is the current node's left child, has parent current node. Same, and I'll be simply offering this in the queue also for proceeding further operation. Great. That is, I'll be passing this left node of the current nodes. Same thing goes for the right tree as well. That is, if current node dot right is not equals to null, in that case this will also be getting inserted in the parents map. That is, current node's right is the child and the current node itself is the parent for the current node's right child, and this would be getting offered or the inserted in the queue for the further processing, because it's not null, so it can be the potential node for further processing. Great. In this way, what I would be having, I would be having this parents at the end updated with the stuff which are required. This is the this thing also we can do. This thing also we need to traverse the whole tree in order to determine the parent mapping stuff. Great. So let's say for now I'm just simply commenting it out because I have already wrote the in order code over here. Great. I do have build parent. I have called this. Now the parent will be having all the referencing which we have talked over here in this case. Great. Now the step two is what? I need to do the BFS from target. So over here, let's start with the BFS from the target. And also for to stop at distance K, I should have this pointers, this increment stuff. So I can stop at a provided K to me. In this case, it was 2. Great. So okay, this thing I need to do over here. First thing is that I will be requiring distance variable to determine that up to what distance I have already traveled. Great. And also to do the BFS stuff, I would be requiring Q over here that will store tree node. Let's name it as Q only. And the new linked list implementation class that I'll be using over here. Great. The very first node I will be passing is that uh, target, because we'll be starting with the target, because over here we have seen in this example we have started with this target 5 provided to us. Great. So I would be doing until my queue is not empty, and then over here the very first node, it means the very first thing I would be like, okay, here I have offered this target node, this is a distance 0. Now I'll be proceeding, moving further with the distance 1. So I need to do very first thing is that I need to increment the distance, okay, kind of stuff and all those things. But before doing all these things, I need to traverse from 0 to 1 step. Great. I need to traverse from 0 to 1 step. Okay, distance plus plus, but before this I need to traverse from 0 to 1 step. Great. So okay, so what's I need to have a queue size. That is, it will determine, okay, at the particular level what all nodes are there, what's the size of it. That will be getting determined from this queue size, and it will also help in the in the internal traversal. Great. So the queue dot size will be determined by this. Great. So I'll be doing an iteration of it in order to do the for the level order traversal. It and I is equal to 0 as less than q size I plus plus. Great. This thing I would be doing. Now at each iteration I will be determining tree node, that is the current node, that will be what, q dot pole, which we are doing in the dry run. Great. Now I need to do what, I need to figure it out, which we discussed, that is ready layout. From 5 I went where, 6 2 and 3, that is left, right, and then parent. Great. Here also I'll be doing the same thing. Great. So the first thing which I'll be doing, I'll be checking with the left. Okay, does current node uh, has left, if it's not equal to null. And also I should have visited set. Great. In order to determine, okay, which node has been visited, which node has not been visited, in order to avoid the looping kind of stuff. Great. So over here, so that's the dry run helps us in the coding. If we understand this, then the coding part would be much more easier, because here itself 70 to 80% of our problems get solved, and the coding part is just we need to write it in the whatever the coding language, program language which we prefer. Great. So here I'll be having the set tree node in order, and it will be denoting what all nodes has been visited. So I'll name it as visited with the implementation class of has set. Great. And over here, the very first node that will be visited will obviously the target node which I does have over here, because from start that node only I'm starting out. Great. And I also need to check over here what if it is not equals null. Great, means it has some node, and also it should not be visited. So me say if visited does not contains this node, which node currently I'm referring to left of current node. Great. If it is the case, then it might be the potential answer, so I need to offer this in the queue. Great. So I'll be offering this current nodes left in the queue, and also now this is, has been offered for the queue, so now it is visited as well, so I will be adding in the visited set as well, that is current node dot left over here in this case. Great. Now I'll be going with the uh, right node. So over here, if current node dot right is not equals to null, then I need to proceed with the right. But before that, also I need to check whether it is available in the visited set or not. If it doesn't if it doesn't contains with this node, then okay, I can be sure that okay, this is not visited yet, so I can proceed further. I can just simply offer this in the queue, that is queue dot offer current node dot right. And also if I'm offering this in the queue, then I can also say that okay, this is visited, so that's why I would be adding that in the visited set as well, that is current node dot right. Now it's the time to go parent part, for which we have did all this kind of complex stuff. I need to go radially outwards as well. So now it's time for the parent. Great. So now here I would be requiring what I would be requiring to have. Great. So firstly I need to determine who is the parent of, okay, who is the parent over here in this case. So I need to of this current node, over here. So over here I need to check this out from where, from this we have built a parent, and it is there in this parent. I will be finding it is out in the from this, it will definitely have this parent value, parent node, which node it refers to. Okay, great. I would be saying what, uh I need to get, okay, who is the parent of this. So I'll be saying parents dot get, and the key which I'll be passing is this current node. Who is the parent of the current node? I would be saying what, if parent is not null, then only I will proceed further. Now why should I enter insert null in my answer if it is not null, and also if it is not in the visited set, then only I will be moving further with this particular parent of the current node. If it is the case, then I'll be offering this as well to the queue, and because it's visited, then I need to add this in the visited set as well. And now this, I have started out with the target node 5. I look around left, right, parent. Now from this denotes that okay, one step is done. So over here I'd be doing distance plus plus. Great. So I would be keep on doing this thing until when I should stop. When distance becomes equals to the provided k value, and over here is 2, but I can't be sure that okay it will always be 2, so I need to compare it with the k, like okay, if distance is equals to k, I need to stop then and there itself. Great. So what I'll be doing over here is this. I'll be saying, okay, if distance is equals to y equals to provided k, break, don't execute further, break this loop, its whole loop itself. Great. Now in this way, I would be having what I would be having at the end. I'd be having all the potential nodes in the queue, but I don't have to return queue, I need to return list. So I would be poll doing the poll of all these nodes 7, 4 and 1, and inserting it in the list, and I'll just simply return it, because that's the answer which is expected in this problem statement. So that I could simply do by this thing. Great. Over here I'll be simply saying, okay, I'll be running a loop for, not for, why there is no need to write a for loop, while my queue is not empty. While my queue is not empty, I can just simply do one thing, is that in my result I'll be adding whatever the element or whatever the node I'll be getting after the polling of queue. Simple. And at the end I'll be simply returning a result, because this is the code which we wrote. Let's try this out whether it is getting accepted. Let's firstly run it and see. Okay, it gives us an error that it says, when I'm inserting queue.poll, queue consists of tree node over here, and I'm pulling this out and inserting in the result list. And the result list, it accepts integer, and I want to return the list of integer. It doesn't care about nodes, because there might be the possibility that, okay, there can be two nodes. So let's say, this is a 3, and let's say this is also a 3. In this case, these two nodes are different, these are not same, these are different. This node and this node are different. So I need to do that case. That can be the case. Okay, it's asking for in the integer, so I'll be saying, okay, q dot poll and then dot val. So that will be getting satisfied, I guess. Let's try this out again. Run. Let's click on run. Now also in my uh, parent building, I just mistakenly wrote pro node's name. It was root, not the any kind of node. So now I think that it should work. Let's click on run. Okay, it has been accepted, all the two test cases. Let's minimize it and let's try to submit it. Where it's getting submitted, or it's getting TLE or something like that. Great, it has been submitted. Great, it works. So this was the about the this problem, that is all distance nodes k in binary tree. But before winding it up, I also want to talk about one thing, and that is time complexity. Complexity is over here. Great. So the complexities over here is that, firstly we'll be looking into the time complexity. So the time complexity which is required over here is that, big of an why is this, for the parent mapping I required big of an, and for the BFS traverser I required big of an, which is big of 2n, which eventually becomes big of n only. Great. That's the time complexity which we would be requiring to in order to solve this problem with this approach. And then the space complexity would be what? It would be, let's check this out. So here We are used parent map big O of n q plus visited big O of n, which ultimately becomes big O of n only. As you can see over here, visited set, parent map, maps, and q, which eventually becomes big O of n only. So space complexity would also be big O of n over here in this case. Great. And also, we were winding it up. I want to give certain notes for this is that uh, if an interview says that all nodes at distance k, means if there's an in the problem statement, so your brain must fire this thing that okay, I need to do the graph conversion, I should have band mapping, I should do bfs from target, there should be visited set, and why there should be visited set, because of the in order to avoid that looping stuff, and I had to stop at level k. I don't need to do infinitely, I don't need to traverse the whole I need to stop at level k. And also, the common interview traps are that you are trying DFS blindly, and you are forgetting parent traversal, because here we do have access to left and right, but we should be requiring parent reference as well in the future. That's now we have looked around. And also, uh, no visited set kind of stuff. You should have this thing, because you might forget in the interview, or whenever this problem is getting used in the actual in the real scenario. And you might be off by one in distance counting, so you should uh, keep these all these points in your mind. And this here, what we have learned in this problem, that this problem matters a lot, because this problem teaches turning trees into graphs. And also we have mastered bfs in some up to certain level. And also we have went to the distance based reasoning, that how this distance can be help in solving this problem. And also another problem as well, that is burning tree, and a lot of stuff, or a lot of problems available out there. And we have also learned that the control traversal, which we need to achieve in this, that is upward, we have achieved over here, that is upward movement ability by approaching this solution approaching this kind of pattern, and solving in this way while building intuition. So that was it from my side. Thank you. Thanks for watching. See you soon. It was me, Deepak Chaurasia. Bye bye.